Hi, everyone, and welcome to this episode of Foundry Fireside. My name is Lori from the Foundry Communications team, and today I will be chatting with one of the Foundry's postdocs, Sean Mills. Sean works with Professor Andrew Miner's research group at the Foundry's National Center for Electron Microscopy using electron microscopes to study material defects. All right, Sean, how about we get started with you telling us a little bit about your project?
Hi, Lori, and thank you for having me on the Fireside Chat. My project is related to nuclear materials that are exposed to a series of degrading effects. These are kind of happening in unison. So these include high temperature and corrosion, so rusting, that kind of behavior, and then also irradiation. So as these are all happening, we want to be able to kind of characterize what's going on in these primarily metal systems using microscopy techniques. And so that's what I work on here at the National Center for Electron Microscopy. This is a part of a larger project affiliated with several other labs. It's called the Future or Fundamental Understanding of Transport under Reactor Extremes. And it's an EFRC under Basic Energy Sciences Office. And so right now, what we're focused on is using high resolution scanning transmission electron microscopy to identify these really small scale, these atomic scale defects that are essentially the driving force for many of these processes.
Wow, that's really interesting. So what's the hope for this project? What are you hoping to find?
Everyone wants to have the best information about when things might fail. My graduate research was focused on the fatigue and fracture in aerospace metal alloys. And so this work is a little bit different in its problems, its mechanisms of corrosion and irradiation and how these work into degrading the material. But the general concepts are the same in order to figure out when these parts might fail. In this case, we have components inside these complex nuclear environments that are working in unison to degrade the material. These are stainless steel alloys, nickel-based alloys, and we want to determine mechanisms of failure that allow us to generate models and when things might need to be replaced, and when we want to design new materials for these next generation reactors.
That's super cool. So what makes you most excited about this topic?
Material science has always been exciting to me based off of its interdisciplinary nature. On a daily basis, we're using physics and chemistry and mechanical engineering to really tackle these really fundamental problems. And in corrosion, this is related to several industries, including batteries, computing, the auto industry, aerospace, and nuclear technology. These fields can all benefit from these high-resolution characterization techniques. And being able to observe these nanoscale features is really at the cutting edge of this industry. Can we simulate these really complex environments at a very small scale? Not only is the problem been really unique, but also the environment that I get to work in on a daily basis has really made this extremely rewarding. NSEM is a great place to work with others, and both in peers and faculty alike, to really uncover these really challenging problems and find solutions for them using instruments and talking with everyone to figure out exactly how can we better tune these experiments and investigations.
That's really awesome. So why this area of research? How did you get into this field?
Well, I have always been interested in science and engineering and mathematics. Really, to start out, I had a big influence from my parents. They are both engineers and have always pushed me to excel in my schooling. I've always been interested in science, and fortunately enough, I was able to take a couple of courses in high school that allowed me to really discover material science as a field. That pushed me to explore further in my undergraduate degree, and then really hone my skills and hone my focus to microscopy in graduate school, where I was able to more readily use scanning electron microscopes and transmission electron microscopes to really tackle these problems that I was faced with as a graduate student.
Okay, I have one last question for you. What's the next big question or the next big step for this project?
So in this project, we've been focused on designing materials to simulate corrosion and irradiation and high temperature effects in order to best represent what's going on in a nuclear reactor and what these materials are actually facing in reality. So currently, we've been focused on just corrosion and just irradiation, just high temperature effects, but we really want to bring them all together into one unified experiment in order to simulate exactly what's happening in these coupled effects. So the effect of irradiation and corrosion damage, and being able to observe this all at once. And so that's really what the in situ TEM approach allows us to do, in order to say whether we advance or limit this corrosion effect.
Nice. All right. Thank you so much, Sean, for taking some time to talk to me about your work. It's super interesting. It's been cool to learn about. And for all of you joining us today, thanks for watching. And I hope you stay tuned for more episodes of Foundry Fireside.